Hello everyone, welcome to another episode of Math-321. So today we're going to start investigation 26, which is on cosets and Lagrange's theorem. Okay, so here are our focus questions for this investigation. What are left and right cosets? What are some important properties of cosets? How do cosets partition the groups on which they are defined? What important fact does Lagrange's theorem tell us about subgroups of finite groups? And finally, what are some consequences and corollaries of Lagrange's theorem? Okay, so let's start off with a preview activity. And just to motivate this activity a little bit, in investigation 23, we learned that in a finite cyclic group of order n, there is exactly one subgroup of order m for each positive divisor m of n, and these are the only subgroups. So in this investigation, we're going to try to find out whether this is true of all groups or what parts of it could be true for all groups. So go ahead and pause the video and try this preview activity, and then we will go over the solutions. Okay, so let's go over part A here. Find all the non-trivial proper subgroups of D3. Remember, D3 is the symmetries of the triangle. How are the orders of these subgroups related to the order of D3? Okay, so this is maybe a little bit tricky, first of all, just to find all the subgroups of D3. But let me explain the logic of how you would do that. So first of all, D3 can be written as these 6 elements. So we have I, the identity, R, that's the smallest rotation, and then R squared, that's doing the rotation twice. And then we have R, which is reflection over a vertical line, and we have little r, big R, that is another of the reflections, and then little r, big R squared, that is the third reflection. So these ones over here, these are reflections, and these ones over here are rotations. So one thing you can note is that if you get either capital R or capital R squared in your group, then you must have all 3 of those rotations in there. So as soon as you get one of those 2, capital R or capital R squared, that brings in the other rotation. So one of the subgroups will be the following. So just the 3 rotations, that's a subgroup. And then other subgroups would be just a single reflection and the identity, because each reflection is its own inverse, and so that will be closed, and it will contain inverses, and then it'll have the identity. And of course it'll inherit associativity from the larger group. So you get these 3 that are just the identity and the reflection. And then this is actually all of the proper subgroups. So the reason there are not any more is because if you put 2 different reflections in there, then that will actually give you one of the rotations. And then once you have all 3 rotations and 2 reflections, then you automatically get the other reflection as well. So that would be the entire group. So it's just these 4. And so the orders here, is 3, 2, 2, and 2. And then the order of D3, of course, is 6, because it has 6 elements. So we see that the order of the subgroups... Sorry if you guys can hear my cat sneezing. He insists on being in these videos. So the order of the subgroups here does actually divide the order of the group. And we do have a subgroup for every divisor. And that was also what we saw with cyclic groups, that there was a subgroup for every divisor of the group order. So now let's look at part B. Okay, so for part B, for each divisor m of the order of D6, does D6 contain a subgroup of order m? If yes, exhibit a subgroup for each divisor. If no, explain why. So first of all, the order of D6 is 12, so it has 6 reflections and 6 rotations. And just D6 itself can be written like this. So it's I, and then the first rotation, and then rotating twice, rotating 3 times, 4 times, and 5 times. And then of course if you go 6 times, that's all the way around because it's the hexagon. And then you have these ones, so oops, just vertical reflection by itself, and then with 1 rotation, 2 rotations, 3 rotations, 4 rotations, and 5 rotations. Okay, and then so the divisors of 12 are 1, 2, 3, 4, 6, and 12. Okay, so there is a subgroup of order 1, which is just the identity. There is one of order 2, in fact there's a whole bunch. So each of those reflections will be a subgroup with the identity. And then order 3, there's at least one, I'm not sure exactly how many there are, but there's this one, for example, there's I, and then r squared, and r to the 4. Okay, that will form a subgroup. That's a cyclic subgroup, actually. And then there is one of order 6, that's all the rotations. So identity, and then all of these. And of course, for order 12, there's the entire group. It's a subgroup of itself. But so the only question really is there one of order 4? So a subgroup of order 4 would be, for example, I, and then r cubed, and then little r, and then little r cubed. Okay? Okay, so now let's get a little more into the meat of this investigation. So the subgroup structure of a group tells us a lot about the group. We completely classified the subgroups of cyclic groups, but the previous activity tells us that we can't classify the subgroups of all groups as easily as we did for cyclic groups. So just to expand on that a little more, in the previous activity, we did find that we had a subgroup of the size of each divisor of the group order, but they were not unique the way they were for cyclic groups. So that already tells us this is going to be a little bit harder. Okay, so many important proofs regarding subgroups involve counting arguments. So in order to count the elements of a group, we usually arrange them into disjoint subsets so that we can avoid double counting elements. Cosets are an important example of this technique, and that is going to be the first topic of this investigation. So let's get into it. Okay, so let's start off by defining a relation in groups. So this relation is going to be defined by analogy with the modulo n relation that you're familiar with for integers. So let's just talk about that a little bit first. So recall that if n is a positive integer and a and b are elements of the integers, we say that a is congruent to b modulo n if and only if b minus a is a multiple of n. So another way to rephrase that to make it a little more similar to groups is we could rephrase this by saying that a is congruent to b modulo n if and only if b minus n is an element of nz. And this notation nz, it stands for, it's basically exactly what it sounds like. You're multiplying everything in the integers by n. So it's that set where you multiply the integers by n. So you're getting all the multiples of n. And that is actually a subgroup of G. So the advantage of this version of modulo n relation is that we can extend this to any group, not just Z. So let's look at this a little more deeply. Okay, activity 26.2. So go ahead and pause the video and give this a try, and then we will go over the answers next. Okay, so let's go over this activity. So let H be the subset of Z8, defined by H is the cyclic group generated by 4, which consists of just the elements 0 and 4. Define a relation, I'll call this tilde H, I guess, tilde H relation, on Z8 by A is related to B, if and only if B minus A is in H. Find all the elements of Z8 that are related to 2. Okay, so what we're looking for part A here is we're looking for let's call it, I don't know, B, such that 2 is related to B. In other words, that would mean 2 minus B. Actually, it's the other way around, isn't it? That would mean B minus 2 is in H. Or another way to say it is B minus 2 equals 0, or B minus 2 equals 4. Okay, so I think now that I've restated it in this last form here, it's a little easier for me to see what to do. So let me look at this one first. So what are all the elements that if I subtract 2, I get 0? So we're talking about 0 in Z8, of course. So let's see, I think we could have 2. Let's see, there would be other things like 10, for example, but I'm going to just stick with the numbers from 0 to 7. So I think that's going to be the only one. Okay, so just 2. And then for this one over here, that would be 6, and I believe that is also going to be the only one. So we get that 2 is related to itself under this tilde h relation, and 2 is related to 6 under this tilde h relation. So that's part A. Okay, so continuing on, we're going to do the same thing we did in part A, but for all of the different elements. Okay, so we found that, oops, sorry, losing control of my pen. So we found that 2 was related to 2 itself, and that 2 is related to 6. Okay, so now let's do this for the other elements. So of course, let's see, 3, let's do that one next. 3 will of course be related to itself, because 3 minus 3 would be 0. And then what would we subtract 3 from to get 4? That would be 7. So 3 will also be related to, oops, I put the h on the wrong side, also related to 7. Okay, and then we could do 4. So it looks like for all of these, they're going to be related to themselves. And then the other one would be, let's see, what minus 4 would give us 4? So I think that'll actually be 0. Right? 0 minus 4 is negative 4, and then that's the same as 4 in Z8. So that'll be related to 0. And then I hope that you're seeing the pattern here. They're all just kind of going the same way. So you get the element itself, and then you get the element either plus or minus 4. So this will be, so what minus 5 would be 4, that'd be 9, and 9 is the same as 1. So this will be 1. So when I do 1 minus 5, I get negative 4, which is the same as 4 in Z8. Oops, I wanted to put that here. Although I think it's symmetric, so it doesn't matter that much, but oops. Oh man, I'm really messing up this notation. Okay. And then let's do 6. So that's related to itself, and then what minus 6 equals 4. So 10 minus 6 equals 4, and then 10 is the same as 2 in Z8. Oh, I'm doing it again. I'm putting these backwards. I wanted to do it like this. Okay, and then 7 is related to itself because 7 minus 7 is 0, and then 11 minus 7 would be 4, and then 11 is the same as 3. And I'm doing it again. I wanted to put 7 and put the 3 there. Okay, and then finally the last two, oh no, the last one is going to be, oh no, the last two, I'm sorry, I'm really all over the place, I'm sorry guys. So the last two will be 0 and 1. Okay, so this will be 0, and this one will be 1. Okay, and then what minus 0 equals 4? So that would be 4. So 0 is going to be related to 4. and then what minus 1 is 4, so that'll be 5. So 1 will be related to 5. Okay, hopefully I did those correctly. And you can see a really strong pattern here in the way these work. So everything is related to itself, and then everything is also related to whatever. Okay, so part C here. Let bracket G denote the set of elements in Z8 related to G. List 3 different things you notice about the collection of sets bracket G for G in Z8. So I think maybe we should just list off what these are first of all. So this was 0 and 4. This one was 1 and 5. This was 2 and 6. 3 and 7. So that was 4 and 0. And then, so actually this one, what I'm noticing is that that is actually the same as bracket 4. And then for 1, this was also the same as bracket 5. And this was the same as bracket 6. And this was the same as bracket 7. So what you can notice here is that these are all disjoint or identical. So in other words, for example, bracket 0 and bracket 4 are exactly the same, but unless 2 of these little bracket sets are exactly the same, then otherwise they are disjoint. So these actually form a partition of Z8. And remember, a partition, if you've forgotten from your discrete structures class, a partition is a collection of subsets where the union of them equals the larger set, and they are otherwise mutually disjoint. So in this case, these 4 sets here that I'm underlining, that is a partition of Z8. Okay, so let's extend this idea to more groups and more operations. So we can extend the idea of the modulo n relation and the tilde h relation to any group. But most groups are written with multiplicative notation, and most of them are not abelian, so we do have to be a little bit careful with the notation. So we're going to be using this notation of A inverse B rather than B minus A, like we did on the last activity. So B minus A, if you were to write that in multiplicative notation, it's a little bit tricky to say whether you should put the minus A first or the B first, since additive notation is abelian, but there are some, it's just more like traditional that the A inverse goes first, so we'll put the A inverse first there when we extend this to multiplicative notation. Okay, so anyway, definition 26.3, let G be a group and H a subgroup of G. Let tilde H be the relation on G such that for all elements A and B of G, A is related to B by the tilde H relation, if and only if A inverse B is an element of H. So this is just like what we were doing on the last activity, except instead of being B minus A, it's A inverse B. So it's when A inverse B is an element of the subgroup. And then oftentimes the subgroup will be clear in context and we'll just write tilde instead of tilde sub H, but sometimes we might have to talk about more than one subgroup at a time, and then we'll put the subscript on there. Okay, so let's go ahead and do another activity, activity 26.4. So I just put the definition of the relation back up there for you, and then the activity is below. So go ahead and pause the video and try this, and then we will go over it. Okay, so now let's go over this activity. So let G be equal to S3, so the symmetric group on 3 elements, and let H be the cyclic subgroup generated by the cycle 1, 2. Find all of the elements alpha in S3, satisfying alpha is related to the cycle 1, 2, 3. Okay, so let's go over a few things here. So first of all, let's write out what the elements of S3 are. So the elements of S3 are the following. So there is the identity, which you can write as I, or is the cycle just containing 1. And then there are 3 permutations. So there's 1 and 2, there's 2 and 3, and then there's 1 and 3. And then there's two cycles of length 3, so there's the one that goes 1, 2, 3, and there's the one that goes 1, 3, 2. Okay, so that's S3. And then what is this H group? So H is generated by a permutation, and a permutation is its own inverse. So this H group is just going to contain the identity and then 1, 2. Okay, so all the powers of 1, 2 are either the identity or are 1, 2 itself again, just that transposition. Okay, so now we're looking for all of the elements alpha that satisfy alpha is related to 1, 2, 3. So let's translate what it means for alpha to be related to 1, 2, 3. So what that means is that alpha inverse times the cycle 1, 2, 3 would be in H, or in other words, it would be in this subgroup that is the identity and the cycle 1, 2. Okay, so there's actually only going to be 2 answers here. So there's going to be one element alpha that gives us the identity, and then there's going to be one alpha that's going to give us this cycle 1, 2. Okay, so we just have to solve these 2 little equations. So we need to solve alpha inverse 1, 2, 3 equals the identity, and solve alpha inverse 1, 2, 3 equals this transposition of 1 and 2. Okay? Okay, so what I need to figure out here is, okay, what can I do here? So let me try doing this. Let me try multiplying both sides here by alpha on the front, like this. And then I'll have alpha I. Okay, so this alpha and alpha inverse are going to cancel. So this one I can actually just solve really quickly like this. So that's one alpha. And then the other one, let me try, let's see. So if I multiply both by alpha again, like this, 1, 2, 3, and then alpha 1, 2. Okay, so those will cancel, and then I'll have 1, 2, 3 equals alpha 1, 2, and then if I apply the inverse of 1, 2 to both on the right, I'll get this 1, 2 inverse alpha 1, 2 1, 2 inverse. Okay, so we can just solve for alpha like this. That's the nice thing about groups, is that you can solve for things in them. I mean, that's the whole point of why they were invented, to make solving equations easier. Okay, so now we just have to figure out what this is. So what is the inverse of the 1, 2 transposition? That's just going to be 1, 2 again. All transpositions are their own inverses. So now I'm just going to simplify this into one element. So let's see. All right, so let me think about where 1 gets moved. Okay, so 1 gets moved to 2 in that transposition. Remember, we applied the permutation that's on the right first. So 1 gets moved to 2 there, and then when I apply this one, 2 gets moved to 3. So this is going to send 1 to 3. And then where's it going to send 3 to? So 3 doesn't get sent anywhere in this one. And then by this one, 3 gets sent to 1. So, okay, so that's just 1, 3. And then where does 2 get sent to? We could check that as well. I don't think it's being sent anywhere. But let's see, 2 goes to 1 in here, and then 1 goes to 2 in here. So 2 gets sent back to 2. Okay, so this alpha is just the transposition 1, 3. All right, so that is the answer to this activity. Okay, so here is another activity for you to prove that the tilde relation is reflexive, symmetric, and transitive. And if you forgot what those things are, I put the definitions of them in the parentheses there for you. So go ahead and pause the video, and then we will go over it. Okay, so let's go over this activity. I think I'll be able to squish it all on this slide. So let G be a group with identity E and H a subgroup of G. Prove that tilde is a reflexive relation on G. That is, for all A in G, A is related to A. So, okay, so I'm going to start by letting, so I'm starting with this for all statement here. So I'm just going to let A be an element of G. And now I need to show that A is related to itself. So what I need to do there is to show that A inverse A is an element of H. And this is really easy because A inverse A is the identity, and that's in H. So you automatically get just almost immediately that A is related to itself. And the reason the identity is in H, of course, is because H is a subgroup. Okay, so the second one here, prove that tilde is a symmetric relation. So in other words, prove that for all AB elements of G, if A is related to B, then B is related to A. So I'm going to translate the for all statement here into a let statement. So let A, B be elements of G. And now we're trying to prove an if-then statement. So we're going to start by assuming the if part. So assume A is related to B, and then we're going to show the then part. So I want to show that B is related to A. Okay, so what do I get from this assumption? What does this tell me? This tells me that A inverse B is an element of H. And remember, what I'm trying to show is that B inverse A is also an element of H. So I think there's a special little trick that I can use here that'll make this easy. Then H is a group, so it contains inverses. So it contains A inverse B inverse, like that. And what is that going to be? So remember, when you take the inverse of a product, when your group is not abelian, you have to swap the order and then do the inverse of each one. So this is going to be B inverse, A inverse, inverse. Just like with matrices, you reverse the order and then apply the inverse to each one. So this is going to be B inverse A, and that means that B is related to A by the tilde operation. Okay, the last one, prove that tilde is a transitive relation on G. That is, for all ABC in G, if A is related to B and B is related to C, then A is related to C. Okay, so I'm going to, first of all, I'll translate the for all statement there into a let. So let A, B, C be elements of G. And now I'm doing an if-then statement, so I'm going to assume that the if part is true. So I'm going to assume A is related to B and B is related to C. And now I'm going to try to show the then part. So what do I get from this assumption? So that tells me that A inverse B, oops, sorry, A inverse B is an element of H, and B inverse C is an element of H. Okay, so just looking at those two elements, I think I see how I'm going to end up getting A inverse C. So, because H is a group or a subgroup, that means that it's closed under multiplication. So A inverse B, B inverse C, which equals A inverse C, is going to be an element of H. So A is related to C. And that's it. Okay, so now I'd like to review the concept of equivalence relations a little bit. This is something that you would have gone over in discrete structures. So recall that any relation which is reflexive, symmetric, and transitive is an equivalence relation. And recall also that any equivalence relation partitions the underlying set into mutually disjoint subsets called equivalence classes. So for any equivalence relation tilde on a set A, the equivalence class of an element little a in big A is written like this. It's bracket A, and then that is defined to be all of the elements B in the set A such that little a is related to B. So this is just everything that is related to A. That's what bracket A is. And then, of course, if it's an equivalence relation, then it's symmetric. So this is also all of the things that are related in the other order, like that. And then if A is related to B, we get that bracket A equals bracket B. And if A is not related to B, then bracket A and bracket B will be completely disjoint. In other words, their intersection will be empty. Okay. So now let's talk about cosets, and I'm going to show you a couple of facts about cosets before I actually define what they are. So let G be a group with subgroup H, and let tilde be that relation from definition 26.3. In other words, A is related to B if and only if A inverse B is in H. The equivalence classes of tilde have a special form, and I'm going to show you what that form is right now. So let A be an element of G, and let B be an element of the equivalence class of A. Okay, so since B is in the equivalence class of A, that means A is related to B, or B is related to A in either order because it's symmetric. So that means that A inverse B is in the subgroup H. So since A inverse B is in the subgroup H, that means that A inverse B is equal to little h for some little h, which is an element of big H. Okay, so since we have that, we can multiply on the left of both sides of that equation to get that B equals AH. And then if we let A capital H be defined as this following set here, where it's literally just what it looks like, you just multiply A times every element in H. Then what we can see here is that because B equals AH right there, that means that B is an element of AH, the set AH. So that shows all that I just did in that bullet point there. That shows that the equivalence class of A, or bracket A, is a subset of AH, where that is just the set of multiplying A times everything that's in H. Okay, so conversely, if we think about trying to do the subset the other way around, let B be an element of this AH thing that we've defined. Then B is equal to AH prime for some H prime in H. That's just how the set is defined. If B is going to be an element of AH, it must be A times some element of H. So if H prime is in H and B equals AH prime, then we can multiply both sides of this equation here, B equals AH prime, multiply both sides on the left by A inverse and get the following equation. A inverse B equals H prime. And so since A inverse B equals H prime, that tells us that A inverse B is an element of the group H, or the subgroup H. So that tells us that A is related to B. So that tells us that if A is related to B, then B is an element of the equivalence class of A. And so we started off with B being in AH, and then we found that it's in the equivalence class of A. That means that AH is a subset of the equivalence class of A. So what we've just done is we've shown in both orders that bracket A is a subset of AH, and AH is a subset of bracket A. That means that bracket A equals AH. So the equivalence class of A under this tilde relation is exactly just this thing right here. It's all the elements in the subset with little a multiplied on the left. That's all it is. So the equivalence classes of this tilde relation, they have this form for every element A in G. Okay, so that brings us to the definition of a coset. So let G be a group with subgroup H, and let little g be an element of big G. The left coset of H in G containing little g is the set GH, and that is just defined as little g times every element of H. The right coset of H in G containing little g is the set HG, and that's just every element in the subgroup H multiplied by little g on the right. So it's left if you're multiplying little g on the left, and then it's right if you're multiplying little g on the right. And then the element G itself is called the coset representative of little g H, or H little g. And of course, it could be possible that there's more than one element in G that gives you the same coset. So that's why there's the concept of a representative. But we'll talk about that more later. Do note that this definition is using multiplicative notation. So if your group happens to be additive, then you would write cosets like this. And if it's additive, then there's probably not a concept of left or right because it's probably abelian. So they would just be written like that. Okay, so this brings us to Theorem 26.7. So since the equivalence classes of the tilde relation are exactly those left cosets of H and G, we have the following. Theorem 26.7, let G be a finite group and H a subgroup of G. If A and B elements of G, if A and B are elements of G, then AH equals BH, or AH and BH are disjoint. In other words, their intersection is the empty set. So one of those two must be the case, and that's just a feature of any equivalence classes. And since these left cosets happen to be equivalence classes, that means they have this feature. And then secondly, the group G can be written as a disjoint union of left cosets of H, and that's again just using the fact that these left cosets are the equivalence classes of that tilde relation. That means that they partition the set. That's a feature of any equivalence class. They always partition the set, which means that the set can be written as a disjoint union of the equivalence classes. Okay, so anyway, this theorem, it's actually helpful because it gives us a way to count elements in a group, and we're not going to get to that today, but we'll get to that next time using that fact. Okay, so here's the next activity for you, so go ahead and give this one a try, and then we will go over it. Okay, so let's go over part A here. Find all of the left and right cosets of this group, subgroup H, which is the cyclic group generated by the cycle 1, 2. In G equals S3. So I think it's worth listing again what are the elements of S3. So this is all the ways of permuting 3 elements. So there's the identity permutation, there's swapping 1 and 2, swapping 2 and 3, swapping 1 and 3, and then there's 2 length 3 cycles. There's 1, 2, 3, and then there's 1, 3, 2. Okay, so those are the elements of S3. And we're just going to find all of the left and right cosets of this H thing. So let's just define what H is. So H is going to be the identity, and then just this transposition that swaps 1 and 2, because that is its own inverse, so there don't need to be any other elements in there. Okay, so let's see. So we're just going to go through all of the elements in G and just multiply them on the left and the right by H and just see what we get. Okay, so I'm just going to start with the identity. So identity times H is just going to be, so I'm just going to do identity times identity, and then identity times 1, 2, and so that's just going to be, I mean, obviously it doesn't do anything, it's just H again. Oops, I tried to put commas in there, but there's no commas. Okay, so this is just H again. And then if we do 1, 2, H, so that's going to be 1, 2 times the identity, and then 1, 2 times 1, 2. So that is actually going to be, interestingly, this is H again as well. So this is going to be 1, 2, and then the identity. Oops. Okay, and then if we do 2, 3, so this, sorry, this also turned out to be H. Okay, so if we do 2, 3 times H, that is going to be 2, 3 times the identity, and then 2, 3 times 1, 2. So this is going to be 2, 3, and then let's see, what happens with 2, 3, and 1, 2? Okay, so let me see, where does 1 get mapped to? So 1 gets mapped to 2, and then 2 gets mapped to 3. Okay, and then what happens to 3? 3 goes nowhere, and then 3 goes to 2. Okay, so it's this one. I don't have those all memorized, I just have to figure them out. Okay, and then 1, 3, H. So this is going to be 1, 3, I, and then 1, 3, 1, 2. So this will be 1, 3, and then, okay, so what happens here? Let's see, 1 goes to 2, and then 2 goes nowhere. Okay, and what happens to 2? 2 goes to 1, and then 1 goes to 3. So this is this one. All right, and let's see. So at this point, I think we found the partition. Like, we've gotten 3 different sets here. We got this one, and this one, and this one. So all of the rest of them are going to be equal to one of those 3, because that already partitions G. But anyway, let's keep going. So let's see. Next we have 1, 2, 3, H. So this is going to be 1, 2, 3 times I, and then 1, 2, 3 times 1, 2. So, okay. So we got 1, 2, 3, and then, so I think this is going to be the same set as the last one, but let me just go ahead and confirm. So let's see, 1 moves to 2, and then 2 moves to 3, so 1 moves to 3, and then where does 3 move? So 3 moves nowhere, and then 3 moves to 1. Okay, so yeah, that's just 1, 3. Alright, so that's the same as the last one. And then finally 1, 3, 2. So this is going to be 1, 3, 2 times I, and then 1, 3, 2 times 1, 2. So we get 1, 3, 2. And then let's see, okay, so 1 moves to 2. Oops, and then, sorry, 1 moves to 2 in here, and then 2 moves to back to 1. Okay, so 1 doesn't move at all in there. So that means if 1 doesn't move at all, this must be 2, 3. Because that's the only, that is the only element of S3 that doesn't move 1 at all. Okay, so that's that, and then so these two are the same. So we found 2 copies of each of those sets, which makes sense because they're 2 elements each, and we're partitioning a 6-element set, so there must have been 3 of them. Okay, do I need to do the? So these were the left ones. Do I need to do the right ones? Let me just do a couple, and then I'll stop. Okay, so right. So obviously HI is just going to be H again. So let's see, H times 1, 2. Maybe I'll do that one. So this will just be, so I is going to be on the left, and then 1, 2 will be on the right, and then 1, 2, and then 1, 2. Okay, so this is just H again. Let me do just one more. So H1, let me do in order 2, 3. So this will be 2, 3 on the right of all of the elements of H. So this will be, let's see, so I'm getting 2, 3, and then what am I getting for my second element? Okay, so 1 gets moved nowhere there, and then here it gets moved to 2, and then 2 gets moved to 3, and then 3 gets moved nowhere here. So this is going to be 3. Okay, so what's interesting here is we're already seeing that this is a different partition. We're not getting the same partition as on the left cosets, because we have 2, 3, and 1, 2, 3, but up here we had 2, 3, and 1, 3, 2. So that's actually a different partition. So that's interesting. I'll let you do the last 3 as your own exercise, because I've run out of room. Okay, so let's do part B here. So find all of the left and right cosets of H, which is the cyclic group generated by 1, 2, 3. Okay, so first of all, let's figure out, so first of all, let me just list these elements again here, just so I can keep track of them all. So there's 1 and 2, there's 1 and 3, there's 2 and 3, there's 1, 2, 3, and then there's 1, 3, 2. And then as far as the elements of H, what exactly is H? So I know it has the identity because it's a subgroup, and I know it has 1, 2, 3, but what else is in there? So for example, if I do 1, 2, 3 squared, what is that? So 1, 2, 3, 1, 2, 3. That would be, let's see, okay, so where does 1 get moved to? 1 gets moved to 2, and then 2 gets moved to 3, so that goes to 3. Where does 3 get moved to? 3 gets moved to 1, and then 1 gets moved to 2. So this is 1, 3, 2. Okay, and then are there any other elements? We need to just, it's a cyclic subgroup, so we can just keep going and generating more of them. 1, 2, 3 cubed, what would that be? So that would be 1, 2, 3 squared times 1, 2, 3. So that'll be 1, 3, 2, oops. 1, 3, 2 times 1, 2, 3. So what is that? Let's see. So 1 gets moved to 2, and then 2 gets moved back to 1. Okay, so that doesn't move 1 at all, and the only element that doesn't move 1 is the cycle 2, 3. Okay, well I got 4 elements here, so let me just keep going. There might be more. Let's see, so what is 1, 2, 3 cubed? oh sorry, we did cubed. What is 1, 2, 3 to the fourth? Okay, so 1, 2, 3 to the fourth should be 1, 2, 3 cubed times 1, 2, 3. So I just found out that 1, 2, 3 cubed is 2, 3. So 1, 2, 3. Okay, so what is that? Okay, so let's see here. 1 gets moved to 2, and then 2 gets moved to 3. So this moves 1 to 3. And then where does 3 move to? 3 gets moved to 1. And then 1 doesn't get moved anywhere here. So 3 gets moved to 1. So this is just 1, 3. Oh, okay. I've gotten so I've gotten 5 elements now. So I think there's probably not going to be just 5. I think there's going to be all 6 elements in here. So let me just confirm that that is the case. So 1, 2, 3 to the fifth should be 1, 2, 3 to the fourth times 1, 2, 3. So this is going to be 1, 3 times 1, 2, 3. Okay, so this is going to be, all right, so where does 1 get moved to? So 1 goes to 2, and then 2 goes nowhere. So this is 1 goes to 2. And then 2 goes to 3, and then 3 goes back to 1. So 2 goes to 1. So this is just 1, 2. Okay, so yeah, in fact, H is the entire group. H is G. So that means that GH equals HG equals G for all G in G. Okay, so let's look at part C. If G is any group and H is a subgroup of G, must the left coset of H containing little g be the same as the right coset of H in G containing little g? So this is going to be no, and I think our part A actually contained counterexamples to this. So in general, this is not the case. So for example, I think we had something like 2, 3, H was not equal to H 2, 3. Okay. All right, so now let's look at activity 26.9. So in each of the cases below, write the group G as a disjoint union of left cosets in the subgroup H. Okay, so go ahead and pause the video, try this activity, and then we will go over it. Okay, so let's go over part A here. So we're writing the group G as a disjoint union of left cosets of the subgroup H. So here our group is Z16, and H is the cyclic subgroup generated by 4. And then it's important to recall here that for additive notation, a left subgroup is this type of thing. So it's little g plus H rather than little g times H. And this just means the same thing that you would think that it means. So it's little g plus little h for all H in big H, like that. Okay, so let's establish what H actually is. So H, which is cyclic subgroup generated by bracket 4, that is just simply going to be bracket 4, and then bracket 4 plus 4, or 2 times bracket 4, which is 8, and then 3 times bracket 4, which is 12, and then 4 times bracket 4, which is 16, which is actually 0. Okay, so that's what H is right there. And then so all of the left cosets, they look like just taking those 4 elements and then adding a single number to each of them. So like for example, 1 plus H would be 5, 9, 13, and then 1. 2 plus H would be 6, 10, 14, and 2. And then 3 plus H would be 7, 11, 15, and 3. Okay, and that actually covers all 16 elements. I think you can see we've written all 16 of them now. So we can write Z16 is the union of all of these. So it's, so for the first one I could call it 0 plus H, like that. So that's the original one. And then union 1 plus H, union 2 plus H. Oops, forgot my brackets. and then 3 plus h, and that is all of them. So that's the whole Z16 there, and that's called a disjoint union because it's a union, and the four things in the union are disjoint. Okay, so let's go over part B. So our group here is S3, the symmetric group of 3 elements, and then H is that same subgroup that we had been looking at before, which is just the identity and then the transposition 1, 2. Okay, so I'm just going to copy down some things that we'd gotten from activity 26.8, part A, activity 26.8A. So we had the following. We had that IH was the identity and then 1, 2. And then we had that 2, 3, H was 2, 3, and then 1, 3, 2. And then we had that 1, 3, H was 1, 3, and the cycle 1, 2, 3. There's 2 types of brackets I needed there, and that wasn't one of them. Okay, so that covers all 6 elements of S3. So we can say that S3 is equal to IH unioned with 2, 3, H unioned with 1, 3, H. And that's it. Okay, that's it for today, everybody. We'll resume this investigation next time. So just keep working on your test. If you have any questions with that, please go ahead and email me, and I'll see you guys next time.